Hello, welcome back to the Embedded Systems and Applications lecture. In the previous lecture, we started talking about real-time operating systems, RTOS. We specifically talked about processes or tasks and threads. What are the functions of an operating system? What is an operating system? And how does operating system schedule different tasks in a multitasking system? And along the process, we talked about what threads are, and then looked at some examples of real-time operating system that can be implemented on a Cortex M3 microprocessor. In this lecture, we are going to talk about scheduling algorithms. We are going to elaborate on the scheduling algorithms, how tasks are scheduled by operating systems. So let's delve deeper. Now, here is an overview of what we are going to talk about. We will look at some general characteristics of time-based systems. We will look into some definitions of hard time and soft real-time timeliness. And then we will look at some priorities, some criteria on which an operating system decides which task to schedule. So for example, there is a task T1 and there is a task T2 and there is another task T3, all of them waiting in a queue to get access to the CPU or processor. Now it is the job of my operating system to pick one of these tasks to run. Now, how does the operating system do that? On what criteria does an operating system make a decision as to which of these tasks gets access to the CPU? That is the fundamental idea behind scheduling. So there are certain characteristics that we will look at: priority, determinism, and CPU utilization. And then we will look at criteria that an operating system, real-time operating system, uses while scheduling different tasks. We will go into different kinds of algorithms. Just because there are different criteria, that fact gives rise to different kinds of scheduling algorithm, and we will finally look at real-time scheduling constraints. So let's talk about what a time-based system is. In order to understand a time-based system, let's try to understand how time is defined in computer parlance, in operating system parlance. Now, we define two different measures of time. We define what is known as absolute time and relative time. Absolute time is based on real world time. It is not a relative to any computer event or any computer clock. Relative time, on the other hand, is measured with respect to some reference. Now, time is further qualified as either interval or duration. So we just talked about absolute and relative time. Let's talk about the difference between an interval and a duration. So this is important when we are considering real-time operating systems. We want to understand how we define time and how, more importantly, computers use time and understand time. Now, an interval is marked by a specific start and end times. A duration, on the other hand, is a relative time measure. So any time quanta that have same begin and end times they are called equal intervals of time. So delta t, this difference between begin and end time, is called duration. Now, different time quanta with same durations are not equal intervals. So in other words, if we look at time quanta t1, t2 and t3, t1 and t2 have the same begin and end times, so they are equal intervals. Now t2 and t3 have the same length of duration, delta t, but they do not have the exact same begin and end time. So even though they're equal durations, they're not equal intervals of time. So non-equal intervals of times therefore can have the same duration. Now let's try to understand reactive and time-based systems. Now, embedded systems can be classified into two broad categories: systems that are reactive and systems that are time-based. Reactive systems, they contain tasks that are initiated by some event, and this event can be internal or external to the system. So in other words, a reactive system is reacting to an event. It is not, it has no sense of time. So an internal event may be an elapsed time or a time bound on data that has been exceeded. And an external event is the recognition of a switch that has been activated, or an external response to an internally generated command. So the bottom line again is reactive systems are reacting to an event. Now time-based systems are those systems whose behavior is controlled by some kind of time quantity. Now, such a time can be either absolute, as we talked about, absolute to the real world clock, or relative to a specific interval or a specific duration. So, absolute time-based systems, in such systems an action must occur at a specific real-world time. In relative time-based systems an action must occur before or after some reference. Or there can even be time-based systems that are following an interval. An action must occur at a specified time with respect to some reference. So both relative and following an interval time-based systems, they are not absolute in the sense that they are relative to some reference CPU clock or CPU event. So time is a very important quantity, is an important factor in embedded systems, more importantly in real-time embedded systems. So the relevance of time in embedded systems becomes clear when we are trying to schedule tasks and threads. For example, there is a task T1, task T2, and task T3. And then each of these tasks have a certain amount of time needed for completion. So amount of time needed for completion is little t1, little t2, and little t3. So we have to seriously consider this little t1, little t2, little t3, when trying to schedule which of these tasks, t1, t2, t3, gets access to the CPU next. Now, tasks are threads that are initiated with repeating duration between calls or invocations are periodic. Or in other words, tasks are threads that are repeated after every particular interval of time, that are repeated every so often, are called periodic tasks. Otherwise, if they are not repeating after a particular interval of time, they are called aperiodic tasks. Now, the repeating duration is called period. The rate at which, the time interval at which the task repeats itself, that length of time after which a task repeats itself is called a period. And the time to complete a task is called execution time. Little t1. Execution time. Now, an action that must occur by a specified time is defined as hard, or is said to have a hard deadline. Now, in such cases, a missed deadline is considered to be a partial or total system failure. So, in other words, we are trying to understand, we are trying to categorize time-based systems into two categories, into two branches. One that have very strict time deadlines. If a deadline is met, the system is failure, period. There is no leeway in terms of whether it can be less successful, more failure. No leeway. It is either a successful time-based system or a failed time-based system. So if the deadline is really hard and failing to meet a deadline constitutes failure of the system, then such a system is called a hard real-time system, and such a deadline is called a hard deadline. So a hard real-time system is a system that contains one or more tasks that have hard deadlines. Now, such systems may have other tasks that do not have time deadlines. The major focus is on hard deadlines. So, in other words, all I'm saying is a hard real-time system has at least one hard deadline for one of its tasks. And there can be other tasks that are not so hard deadline based. Now, systems with somewhat of a relaxed time constraints are defined as soft real-time systems. Now, such systems may meet their deadlines on average. Some deadlines may be met, some deadlines may not be met. So, soft real-time systems may be soft in several ways. So, relaxation of the constraint that missing the deadline constitutes a system failure. So, in a hard real-time system, if a deadline is not met, the system is a failure. But if we relax this constraint and say, if a major percentage of tasks are meeting their deadlines, then such a system is more or less successful. Then introducing this kind of tolerance to missing specific deadlines can provide some kind of soft real-time characteristics. So, in other words, in soft real-time systems, the evaluation is a gradation rather than pass or fail on a scale of 0 to 10, the system can be graded as either a fail or pass. But in terms of hard real-time system, there is only either a pass or a fail, and there is no scale gradation. So in that sense, soft real-time systems are not a failure if some of the tasks do not meet their constraints. Now, systems with tasks that have some relaxed constraints as well as some hard deadlines are defined as firm real-time systems. Real-time systems are those in which correctness demands timeliness. So here is the fundamental idea why timeliness is so critical to real-time operating systems. And here is the main root cause where real-time operating systems have to have a very well thought out scheduling algorithms. The fundamental need for a scheduling algorithm in a real-time operating system comes from the fact that robust operating systems, robust embedded systems have to respond to very strict time deadlines. So most such systems carefully manage their resources with respect to maintaining the predictability of timeliness constraints. So in other words, a very valuable asset, knowledge to have in a real-time operating system is to be able to predict when my task is going to complete. We will talk about determinism. In the coming slides, that is our ability to predict with certain probability, within certain probability limits as to what task is going to complete within its deadline. So in other words, being able to predict the behavior, specifically being able to predict the timing behavior of an operating system, of an embedded system, is very valuable for a real-time operating system or a real-time embedded system. So let's look at some of the time constraints and some examples of time constraints and their effects in soft real-time and hard real-time systems. So we are looking at the different characteristics of soft real-time and hard real-time system. Now, a soft real-time system may or may not be deterministic. So in other words, we may or may not be able to predict the timeliness, the timing behavior of a soft real-time system. But a hard real-time system is very deterministic in the sense that we as designers are able to predict its timeliness, its timing behavior. So a hard real-time system is very deterministic and is very predictable as well. But a soft real-time system may or may not be predictable, but a non-real-time system is not predictable or not deterministic at all. Now, when it comes to consequences of late computation, a non-real-time system does not care even if the deadlines are met or if certain tasks compute late. It does not matter. But in a soft real-time system, that results in a degraded performance. But in a hard real-time system, that constitutes a failure of the system. Now, that's about consequences of late computation. Now, in terms of critical reliability, non-real-time systems are not reliable. Soft real-time systems, they are reliable, and hard real-time systems, they are very reliable. Now, when it comes to the property of response dictated by external events, the non-real-time systems do not respond to external events. Soft real-time systems, they respond, and hard real-time systems response is dedicated by external events. Now, in non-real-time systems, it is not possible to analyze on pen and paper, using pen and paper, the timing behavior. But soft real-time systems, it is possible to come up with an analytical timing analysis, or sometimes stochastic simulation. But using hard real-time systems, it is possible, for hard real-time systems, it is possible to analyze analytically and stochastically their timing analysis and their timing behavior. So these are the different properties of non-real time, soft real time, and hard real time systems. Now, having an idea of different definitions of time, absolute relative time, and other key definitions, hard real time and soft real time definitions, let us delve a little bit deeper into the idea of task scheduling. So this is extremely important. Task scheduling is extremely important in a multitasking system. We looked at multitasking systems yesterday. There are more than one tasks with possibly more than one threads. And it is the job of the operating system to orchestrate a scheduling of each of these tasks. Now, how efficiently each of these tasks moves through the various queues along the control path is a quantity of extreme importance. Also important is how effectively the CPU is utilized during such the movement of these tasks. These together, they establish the quality of an embedded systems design. Let's go back to the lecture yesterday that we discussed. In a multitasking system, there can be a number of states in which tasks can be waiting. Task T3 could be, for example, currently executing. Task T1, T2, and T4 could be ready and waiting. And T5 could be waiting, for example, for an external event, for an input or output from a peripheral. Task T7 could have already been completed, and task T6 may be just trying to enter into the system. So in other words, the bottom line that we want to understand is there can be many tasks waiting in the queue in each of these states, except the executing state. Executing state has CPU, and for a single CPU or single processor systems, there can only be one task running currently. But in a ready and waiting state, there can be more than one tasks, and they're all waiting in a queue. Now, how efficiently these tasks are moved through the entire queues, through all of these queues, is a property of critical importance. We want to pay close attention to how these tasks are moving. Now, one important consideration is that CPU, that the processor CPU is an extremely valuable resource. CPU time is an extremely valuable resource, and we don't want CPU to be idle for very long amounts of time. We want to keep the processor or CPU busy to the extent possible, as busy as possible. So with that in mind, let's understand that how efficiently a task moves through the various queues along the application and how effectively the CPU is utilized. They are of critical importance to establish the quality of embedded system design. Now, when we are using different scheduling algorithms, different scheduling mechanisms, an essential component of that control strategy, of that scheduling strategy, is to schedule in such a way that the CPU is allocated, CPU is busy most of the time. We want to minimize the CPU idle time. So in a multitasking system, the main objective is to have some or the other process using CPU at all times. We want to, like I mentioned earlier, minimize CPU idle time. Such a scheme maximizes the usage of this resource CPU or processor. Now, which task is running at a specific time when there are many tasks waiting in the queue? When there are many tasks waiting in the queue, which task gets the CPU next? Or which task is currently executing is based on a number of criteria. So the operating system, when picking a particular task to become current, it is evaluating a number of criteria, which could include timing constraints, deadlines, priorities, so on and so forth. But the bottom line is, in a real-time operating system, an operating system is looking at evaluating various criteria to determine which task should get access to CPU next. It is the scheduler's responsibility. Scheduler is a component of the operating system. It is the scheduler's responsibility to ensure that CPU is efficiently utilized. We talked about it in the last class. Among many functions provided by the processor or CPU, by the real-time operating system. Many functions are provided by an operating system. One of these functions is to manage memory resource management. The other function is to manage CPU resource. Processor is a valuable resource, and managing this processor is a job of the operating system. So scheduler is that component of an operating system which manages CPU resource. So scheduler ensures that the various jobs are executed in such an order as to meet any required timing constraints. In other words, it is the job of scheduler to make sure that all the tasks meet their deadlines. Now, scheduling can be based on different criteria, different priorities. Scheduling based on priority determined by the designer of the operating system or the designer of the application. In other words, the real-time operating system looks at different tasks T1, T2, T3, and T4. And then there is a property associated with task T1. Its priority is high or 10. The priority of task 2 is 4. Let's say the priority of task 3 is 15 and priority of task 4 is 7. Now, scheduling can be based on priority assigned by the designer. So these values 10, 4, 15 and 7, they are assigned by the designer of the application. The designer of an application has the a clearest understanding of what task is critical and what task has lower priority, as to which task needs precedence, which task has lower precedence. So the scheduler looks at this designer assigned priority value and comes up with a scheme to schedule tasks based on priority. So this is the fundamental idea behind scheduling using priority. So priority is assigned by the designer and is based on a variety of different criteria. Such criteria are used to resolve which task to execute when more than one task is waiting to execute. So T1, T2, T3, T4 are all waiting for CPU. Which task gets access to the CPU is based on the priority number. Tasks with higher priority execute preferentially over tasks with lower priorities. So we talked about this idea of determinism earlier, being able to predict the timing behavior of an application that is of critical importance. In a real-time context, a task that can be determined to always meet its constraints is said to be schedulable. So in other words, when a scheduler looks at tasks and evaluates and determines that it can definitely meet its deadlines, the scheduler is very happy to schedule it for you. The scheduler is very happy to accept such a task. But if a scheduler of real-time operating system, if an operating system looks at task 5, for example, and determines that it does not meet its time constraints under current situations, then operating system rejects this task. It does not want to schedule this task. So a task that can be guaranteed to always meet its deadlines is said to be deterministically schedulable. Now, such deterministically schedulable task occurs when the event's worst case response time is less than or equal to the task's deadline. So in other words, if we know the worst case response time of a task and if we can ascertain that it is before the task's deadline, then such a task is deterministically schedulable. When all the tasks of a system are schedulable, then such a system is said to be scheduled, or overall system can be scheduled. So that is scheduling based on priority, scheduling based on determinism, and scheduling based on CPU utilization is what we are going to look at now. So in addition to satisfying strict timing constraints, a very important consideration is to keep the CPU busy all the time. Ideally, given that CPU is an extremely valuable resource, CPU time is of the essence. We want to keep CPU busy 100% of the time. But in practical systems, system utilization is 40% for a lightly loaded system and 90% CPU utilization for a heavily loaded system. So a measure of CPU utilization for a single periodic task is given by this quantity UI. So UI is the fraction of the time the task keeps CPU busy. Execution time, EI, over PI, the period of a task. That is a ratio of a measure of a fraction of CPU utilization. And we want the CPU utilization factor to be as high as possible. So in other words, if the period is almost comparable to the execution time, so in other words, if a task takes 10 milliseconds to complete, and if a task repeats every 11 milliseconds, we can predict that CPU is going to be busy 10 out of 11 times. We want this number to be as high as possible. And of course, all of this example and this analysis is valid for a single periodic task. Now, let's talk about scheduling decisions. Two key elements of a real-time operating system design are repeatability and predictability. We talked about predictability and determinism earlier. So the first step in developing a robust scheduling scheme is knowing when a scheduling decision must be made. Now, scheduling decisions are made under the following conditions. When a task or a process switches from running to the waiting state, what happens next? What task goes into the running state next? In that situation, we have to make a scheduling decision. We also need to make, or the real-time operating system, the operating system has to make a scheduling decision when a process switches from from a running to ready state, or when a process switches from waiting to ready state. So these are all the situations when a currently running process terminates. What process, what task gets access to CPU next? So these are all the situations under which the scheduling decisions have to be made. And then scheduling criteria can be either preemptive or non-preemptive. Or in other words, if a task T3 is currently running and T2 has a higher priority, and if it can kick out task T3 from the running state, if it can oust T3 from the running state and can take its place in the running state, then such a system is called preemptive. And if T2 has to wait for T3 to finish, but it cannot oust T3 from the running state, then such a system is called non-preemptive states. So a process keeps the CPU until it decides to release. Then such a system is called non-preemptive scheduling scheme. Now, as I mentioned earlier, there can be a variety of scheduling criteria. Scheduling criteria can be based on user defined, based on designer defined priority. or based on certain definitions of turnaround time, throughput, waiting time, and response time. We will look at these definitions shortly, but for now, understand that scheduling priority can be assigned using various parameters. It can be a priority assigned by the designer, it can be a turnaround time, throughput, waiting time, or response time. Now, scheduling criteria based on priority, the designer must critically assess each task, and then if no task is running or a task terminates, the highest priority task among the tasks will run next. So the priority is assigned by the designer, and the higher the priority, the higher the precedence in running next. This is a non-preemptive. But in a preemptive scheme, if a lower priority task is executing, when a higher priority task arrives, then the arriving task preempts the currently executing tasks, or kicks out or ousts the currently executing task. So the lower priority task is then suspended and then resumes when the higher priority tasks completes, or higher priority task blocks waiting for some resource. So a non-preemptive priority based scheduling algorithm, or a preemptive scheduling priority based scheduling algorithm. Now here is the definition. So we looked at the different characteristics, the different priorities. It can be designer defined priority, turnaround time, throughput, waiting time, and response time. So let's try to understand each of these definitions a little bit more. Turnaround time specifies the interval from the time of submission of the task until its completion. So turnaround time includes all the time spent waiting to get into the memory or queue, or waiting to get into the ready queue, and the time spent using the CPU, or executing on the CPU, or doing input output. So an addition of each of these times, time spent on waiting to get into the memory, time spent waiting in the queue, and time spent executing on the CPU. So all of these are added to give us a turnaround time. So throughput is coupled with turnaround time, the number of processes that are completed per unit time. So throughput is defined as how many tasks can be completed in 1 second. So this really depends on the turnaround time. This is how throughput is coupled to a turnaround time. The number of tasks that can be completed in a given time really depend on how long each task takes. So throughput depends on the complexity of the task. A system may execute very high throughput, but if the turnaround time is excessive, we may not be able to meet all our timeliness constraints. So throughput is coupled to turnaround time in the sense that the number of tasks completed in a given amount of time really depend on how long each of these tasks take to complete. So that's throughput. Now, waiting time can also be a scheduling criteria. Or in other words, just like we wanted to come up with a scheduling algorithm that increases throughput and that reduces turnaround time, we can even come up with a scheduling scheme that really minimizes the waiting time. So in embedded applications, The path a task takes through the system involves a number of different queues. There is an entry queue, there is a waiting queue, there is a ready queue, just before getting into the run state, so on and so forth. So minimizing the waiting time is an important performance metrics in a real-time operating system. So we can come up with a scheduling criteria which tries to minimize the waiting time. We can come up with such a scheduling algorithm. Now, another scheduling criteria, in addition to response, in addition to throughput, and in addition to turnaround time, and in addition to priority, is the response time. For an interactive system, the turnaround time may not be the best measure. Or in other words, for a system that has to interact with outside world, that has to wait for events from the external world or some external factors, turnaround time may not be a good measure of its timeliness. So instead of turnaround time, we define a response time, which is the time from submission to the first response. So the time difference between submission and time response is the response time. The first response is called response time. So the time taken for the first response is not the time to the first output. This is something we have to pay close attention to. First response time or response time is not the same as time to completion or time to output. It is just the time an operating system takes even before it can respond first to a given task. So scheduling algorithms can be based on three categories. Scheduling algorithms can be categorized into interrupt driven, polled, or polled with timing event. So these schemes of algorithms are extremely important for hard deadlines. So let's try to understand each of these interrupt driven, polled, and polled with timing event. This is in some sense pretty similar to the event driven mechanism that we looked at earlier. So asynchronous event interrupt event driven scheduling algorithms are one of the simplest scheduling schemes. Under such an approach, the system is constrained to operate in basic one-line infinite loop until an interrupting event occurs. So there is a while one loop. And then when an interrupt occurs, flow of control jumps from the main program to the interrupt service routine, where the designated task is executed. And then we come back to the main program or while loop. Flow then resumes in the infinite loop. So asynchronous interrupt event driven scheduling algorithms, generally the event originates from an external source. The overall behavior of such a system is not deterministic in nature. We cannot predict its behavior because it is dependent on external event. However, once the event occurs, once the external event occurs, it is pretty straightforward to determine what happens after. So event determinism is very little, but post-event determinism is high for asynchronous interrupt-driven mechanisms. So here is a while one loop, and when an interrupt service routine is generated, the while loop is temporarily paused, ISR is handled, and then we go back to executing where we left off. Now, polled and polled with a timing event are a little different from interrupt driven. This algorithm is the simplest and fastest of algorithms. The polled algorithm is continually testing the value of a signal looking for state change, as opposed to an interrupt driven mechanism which does nothing until an event occurs. One thing we have to understand is a polled scheme of scheduling algorithms is extremely deterministic. An important characteristic of polled mechanism is that the time to respond to an event is really computable and well bounded. We can put an upper bound on the time needed to respond to a particular event. So it looks something like this. An infinite loop, within the infinite loop, there are if-then constructs to test for the state of each signal that is polled, or each peripheral that needs to be polled. Now, there can be also state-based scheduling algorithms which can be divided into milli or more, but these are not extremely popular because the states can be the state space explosion can be a big problem. All right, or in other words, when there are a lot of input variables and when there are a lot of different states, just the complexity or the magnitude of the state machine increases exponentially, and then the state machine grows to an unmanageable, unrealistically large state, very difficult to handle, and the state-based scheduling algorithms are used rather carefully. Using states is not really efficient because of state space explosion for large problems. And then there can be a synchronous interrupt event driven. In case of asynchronous interrupt event driven, the interrupt could have occurred at any instant of time. There is no telling as to when the interrupt could occur, but in synchronous interrupt event driven, the interrupts occur only based on a particular timer. So let's look at scheduling algorithms. Therefore, a very interesting set of problems, as you will come to realize, is time shared scheduling algorithms. In a time shared systems, tasks may or may not be all equally important. There can be some less important tasks and there can be some more important tasks. When all the tasks are given the same amount of time, the schedule is periodic. So in other words, a task T1 T2 and T3 all have 5 milliseconds of execution time. When T1 completes and T2 completes and T3 completes, then T1 comes back after 15 milliseconds. T2 comes back after 15 milliseconds and T3 comes back after 15 milliseconds. Then such a schedule is periodic. When the allocation is based on priority, when the time allocation is not equal, then such a schedule is not periodic. These tasks do not repeat at a regular interval of time. So time shared systems in which the different tasks T1, T2, T3, in which all these tasks share the CPU time can be classified into first come first serve, shortest job first, and round robin schemes. We will try to quickly look at these schemes. First come first served scheme is a really simple algorithm. It is easily managed using a first in, first out, first in, first out queue. When a process enters the ready queue, the task control block is linked to the tail of the queue. So the task that comes first is executed first, and the task that comes next has to wait for the previous task to finish. So when the CPU becomes free, it is allocated to the process at the top of the queue. So in other words, there is a queue. Tasks come and tasks are entered into a queue. The first task at the head of the queue executes first. After this completes, or if this goes into a waiting state, that is when this becomes active. Now, there can be shortest time first. Earlier was first come first served, which is a very simple algorithm. A different mechanism is shortest job first. The operating system, the real-time operating system, estimates the time needed to complete each task, and then the task that needs the lowest amount of time to complete is given higher priority. So let me say that one more time. Let's say there are tasks T1, T2 and T3 that an operating system has to schedule. Then the operating system sees how much time is needed for task T1 to finish, for T2 to finish, for T3 to finish. It seems task T2 is the shortest job. So real-time operating system, the operating system schedules T2 preferentially over T1 and T3. So each task has an estimate of how much time the job will need. Now, an important thing to understand is that this estimate is static. Meaning, once the task starts executing, this time reduces, but the real-time operating system does not take the time remaining to complete into account. It just makes one estimate at the beginning of the scheduling scheme. A more dynamic variation is also possible. Now, there is also another scheme called round robin. Round robin is pretty similar to first come first serve. Let's say there are tasks T1, T8, T3 and T5 in a queue. In a first come first served scheme, T5 has all the time in the world to finish. But in a round robin scheme, T5 has only a limited time quanta, a limited time. And after that time is elapsed, the CPU switches automatically to T3, which is also given the same amount of time. And after that time elapses, T8 occurs. And after that, T1 runs. And after that, T5 becomes currently active. A round robin scheme. The CPU is shared among different tasks for a particular amount of time, and then a circular queue goes back to T5. So if this time slice delta T is increased to infinity, if this is increased to infinity, a round robin scheme becomes a first come first served scheme. Think about it. A first come first served scheme with preemption is round robin scheme. Let me say that again. If the time slice delta t is increased to infinity, round robin becomes a first come first served scheme. So in that sense, they are very tightly related. A first come first in first out scheme, a first come first served scheme with preemption. This is a round robin scheme. Now, scheduling algorithms can be based on priority schedule. Shortest job first, earlier we saw, is a special case of more general priority scheduling class of algorithms. The shortest job first was a static scheduling scheme, but if the real-time operating system was to keep improving the estimate of time needed to complete on a regular basis, on a dynamic fashion, then that becomes a priority schedule. So in a priority schedule, a priority is associated with each process, and the CPU is allocated to the process with the highest priority. Now, when there are two jobs with equal priority, then a first come, first serve or round robin scheme is used between two tasks of equal priority. So such algorithms can be either preemptive or non-preemptive. So we looked at time shared scheduling algorithms. Time shared scheduling algorithms. Now, scheduling algorithms can also be based on certain priority schedule, and scheduling algorithms based on priority schedule can be rate monotonic, earliest deadline, least laxity, or maximum urgency. Let's try to look at these scheduling algorithms. A rate monotonic algorithm is a special case of priority driven algorithm. The priority is assigned based on execution period. The shorter the period, the higher the priority. Now, priorities are determined and assigned at the design time, and they remain fixed during the execution and are said to be static or fixed scheduling policy. So rate monotonic or static. Rate monotonic or static. Now, earliest deadline schemes are a dynamic variation of rate monotonic algorithms. The earliest deadline scheme uses a dynamic algorithm with priority assigned based on task with the closest deadline. The task with the closest deadline has higher priority, and the schedule must be established and modified during runtime. This is what makes the algorithm dynamic. Now, in addition to the task to completion, in addition to looking at the deadline, if we want to make the algorithm a bit more tighter with its constraints, then we add what is known as laxity. Okay. In addition to the deadline, the time to execute a task is also considered. So let's say a particular task has a deadline coming up in 10 milliseconds, and the execution time, the amount of time a particular task needs to complete is 20 milliseconds. Now we have a situation at our hands. The operating system looks at this. The deadline is coming up in 10 milliseconds, but the task needs 20 milliseconds. So if I evaluate this, this is going to be a negative laxity. Such a task does not meet its deadline. So the operating system rejects this task. It does not schedule it. So it's a more smarter, it's a smarter improvement over the um, over the tasks based on earliest deadline. So the least laxity schedule is based on a metric using ascending laxity. We must know the exact value of the execution time, or at least an upper bound on it. The value must be updated with each system change, and then least laxity algorithm can be utilized in systems with a mixture of hard and soft deadlines. Now, we are looking at scheduling algorithms. So to put things in perspective, we looked at scheduling algorithms based on time sharing, including round robin, and including first come first serve and other algorithms. We are also looking at priority schedule algorithms. We are currently looking at the different priority schedule algorithms. One such scheme of algorithms is maximum urgency. So maximum urgency first algorithm includes features of both rate monotonic and least laxity. At first, it assigns priority according to the task's period, as is done with the rate monotonic algorithm. And then, after the rate monotonic scheme is implemented, a binary variable is assigned to determine if the task is critical or not. If the task is critical, then they are classified differently, and non-critical tasks are placed in a different queue. Now, the critical set of tasks implement an additional least laxity scheme on top of the maximum urgent, on top of the rate monotonic. So, rate monotonic plus least laxity, a combination of these two, maximum urgency is rate monotonic plus least laxity. When both of these are combined, we get what is known as a maximum urgency scheme. So these are the different time sharing based scheduling algorithms and priority based scheduling algorithms. Let's quickly finish by looking at certain real-time scheduling considerations. A real-time system may be hard or soft real-time. Task scheduling may be static or dynamic, and for dynamic hard real-time schedule, the process is submitted along with a statement of the time required to compute and to do the input output. If the scheduler accepts the task, it guarantees that the task will complete. Otherwise, if the task is not schedulable, the scheduler rejects the task. A soft real-time schedule is less restrictive than the hard real-time schedule. A soft real-time schedule does not require that critical processes should have priority over the less critical tasks. It does, excuse me. Soft real-time schedule does have a requirement that critical processes have priority over less critical processes. Now, implementing a soft real-time system requires careful design of scheduler and other related aspects of an operating system. So, this finishes our consideration of real-time operating system. We looked at different scheduling algorithm using priority scheme and using time-shared systems. We talked about the different scheduling algorithms based on state-based polled and polling with timing and interrupt based scheduling algorithms. We talked about different scheduling criteria, priorities, turnaround time, throughput, wait time, and response time. And then we talked about the comparison of different soft, hard, and non-real-time systems. So in other words, we looked at the different scheduling algorithms that a real-time operating system has to implement in order to ensure the real-time behavior of a particular application. So in the next class we will take up a different topic, Ethernet. So I will see you back